Anytime you're in the second quadrant, what you're going to do is take the 180 degrees minus whatever angle that they give to you, and that's going to give you your reference angle. Okay, for third quadrant, so you're going to need the terminal side here and the horizontal axis right here. Okay, to get this reference angle right here, what you're going to need to do is take the angle that they give you, we're calling that T, minus 180. It's complete opposite from this one right here. And then if you're in the fourth quadrant, so where the angle terminates, horizontal axis, this little bit right here, that is your reference angle. And what you're going to do is you're going to take the 360 minus whatever angle that they give you. Okay, so in this one, find the least positive angle theta that is coterminal with an angle measuring 800, where theta is going to be between 0 and 360. So what we're going to do is take our 800 and we're going to subtract 360. That gives us 440, which is still outside of the 360, so we'll take 440 minus 360 again. Now give us 80, which would be our final answer. Now notice that if I start at the positive x-axis and I go 800 degrees, that's the same thing as starting at the positive x-axis and going 8 degrees. They have the exact same terminal side, which is right here. Okay? Find a positive coterminal angle alpha with the angle negative 45 such that alpha is between 0 and 360. So we're going to take negative 45, and it says positive coterminal, so I'm going to add 360, and that's going to give us 315, which this is between 0 and 360. Okay, so negative 45 has the same terminal side as 315. Okay, find a coterminal angle with 19 pi over 4 where beta is between 0 and 2 pi. Now first off, we're working with 2 pi, which that's the same thing as 360. But I'm looking at a fractional angle. So I'm going to change this 2 pi to a fraction, which means essentially what I'm going to do is 2 pi over 1, and I'm going to get the denominators the same. Since this is 4, I'm going to multiply by 4, so it'll be 8 pi over 4. That's where this is coming from. Okay, so instead of looking at 0 to 2 pi, we're going to look at 0 to 8 pi over 4. Okay, now because this 19 pi over 4 is bigger than the 8 pi over 4, and we're trying to get something, an angle between 0 and 8 pi over 4, we need to subtract. So 19 pi over 4 minus 8 pi over 4, that gives us 11 pi over 4, which is still bigger than the 8 pi over 4, so we'll take the 11 pi over 4 minus 8 pi over 4 again, and that will give us 3 pi over 4. That will be our final answer. Okay, now determining the length of an arc. So what you need to know is the formula for the length of an arc. That is this right here. Remember, S is arc length, R is your radius, and theta is your central angle. Now, you gotta be careful. You have got to be in radians and not degrees in order for this to work, because this is based on radians. Alright, so find the length of an arc of a circle of a radius 12 inches subtended by a central angle of pi over 4. Okay, so we need S is equal to theta times r. Okay, so r theta is pi over 4, and that's already in radians, so we can go ahead and use that, times 12 inches. So S will be equal to 12 pi over 4 inches. And take out the 12, or take out the 4 within the 12, and you're left with 3 pi inches as your final answer. Okay? Find the length of an arc of a circle of radius 5 feet subtended by the central angle of 220. Now, first off, if we're looking for the arc of a circle, then our central angle has got to be in not degrees, it has to be in radians, but right now it's in degrees. So I need to take this 220 and change it to radians. Okay, so this is going to give me 11 pi over 9. Okay, now I can use my formula. So 11 pi over 9 times 5 feet. This will give me 55 pi over 9 feet. And this would be my final answer. Okay, now the area of a sector of a circle. Okay, now what you need to know here is this formula right here. It's either pi r squared over 2, or it could be half, sorry, I said pi. It could be theta r squared over 2, or it could be 1/2 theta r squared, where r is your radius and theta is your central angle. Now again, theta has got to be in radians and not degrees in order for this to work. Okay, so an automatic long sprinkler sprays a distance of 20 feet while rotating 30 degrees. What is the area of the sector of grass the sprinkler waters? Okay, well first off, we're in 30 degrees and we need to change that to radians. Okay, so this will give us pi over 6. Now we can use our formula. So this would be 1/2 times pi over 6 times 20 squared. Say roughly this would be 104.72 feet squared. And its feet is right here. It got squared when we squared the 20. We could have written feet right inside here. But this would be your final answer. Our linear speed is speed along a straight path and is determined by the distance it moves along its displacement in a given time interval. Okay, it says straight path, but then we're looking at a circle here. So it's like you could nick this circle right here and then undo it or unravel it. Okay, there it is unraveled, and then you can take this and you can lay it flat. So then there's your straight path. Okay, now what you're looking at is this point right here. How fast is it circling on the edge of this circle right here? Okay, so for linear speed, you have the notation v, and here's your equation. It would be s over t. Remember, s is your arc length. So we're seeing how fast this point got from here to here, or within that arc over that time. So linear speed is always going to be length over time, like it is right here. Now, angular speed, speed results from circular motion and is determined by the angle through which the point rotates in a given time interval. Okay, so linear speed is determined by the distance this point moves, whereas angular speed is determined by the angle through which a point rotates. So how fast Did you move from here to here? Did it go really, 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 really slow, or did it go really fast? Okay. So the notation for this would be, this is not a W, this is actually omega. Okay, so omega, and the equation is theta over t. So for angular speed, the units could be radians over time, or rotations over time, or it could be degrees over time. Now, angular and linear speed. So angular speed in radians, or omega, representing the amount of rotation occurring in a unit of time, can be multiplied by the radius r to calculate the total arc length in a unit of time, which is the definition of linear speed. So you can start off with linear, and then use what you know for s, which is r times theta. Replace that s with r times theta like they've done here, and then move r down, and then look at this right here, theta over time. That's the same thing as omega. So you can put linear and angular speed together to get linear speed is equal to the radius times the angular speed, or v is equal to r times theta. Now if we look at this one, the wrist can rotate pi over 2 in 0.045 seconds while holding a tennis racket. What is the angular speed of the wrist swinging a tennis racket? Okay, so we're looking for angular speed, so that's why we're using omega is theta over t. Well, your theta would be this pi over 2. So pi over 2 divided by what time? Well, 0.045 seconds. Divide those two, which you get approximately 35, and that will be your final answer for your angular speed. Part 2. If the radius from the edge of the tennis racket to the wrist joint is 2 feet, then what is the speed at the angle of the tennis racket? Okay? So we're looking at the tip, and we're seeing how fast that tip is moving. So since we just found angular speed, and we're trying to find linear speed, now we can use this formula that has both of them together. So the only thing that we need now is the radius, which they give is 2 feet. So all we have to do is take 2 feet times 35, which was our angular speed that we just found, and that will give us a linear speed of 70 feet per second. Okay. A belt runs a pulley of radius 6 centimeters at 80 revolutions per minute. Find the angular speed of the pulley in radians per second. Okay, so one revolution would be going all the way around the circle. And if you went all the way around the circle, well, that's equivalent to saying 2 pi radians, which is essentially what we're getting at right here. One revolution around the entire circle is the same thing as going to 2 pi radians. So therefore, one revolution is equal to 2 pi radians, which means if I put one revolution over 2 pi, or 2 pi over one revolution, that's a form of 1. Okay, so then we take this 80 revolutions per minute. So here's our 80 revolutions per 1 minute. We're going to multiply it times a form of 1 like we're doing right here. And that'll essentially get rid of your revolutions. So your revolutions get knocked out and you are left with radians per minute. But it said we want radians per second, not radians per minute. So then we need to take this 160 pi over 1 minute and then change it from minutes to seconds. So that would be 1 minute over 60 seconds. So then our minutes will cancel out, and then we're left with 160 pi over 60 radians per second. We need to simplify this to 8 pi over 3 radians per second. That would be your final answer. Okay, part 2, find the linear speed of the belt in centimeters per second. We just found angular speed, so we can use linear speed is equal to radius times angular speed. So we found the angular speed to be 8 pi over 3. All we have to do is multiply times the radius, which is 6, to give us 50.27. That's a short way. or we could use this long way here.